Okay, so let's look at another cooling problem. We're still using Newton's law of cooling. And we have a cake with a temperature of 210 degrees. So that's our initial temperature. This is Fahrenheit. The room, which we know that surrounding air temperatures are C, is 70 degrees Fahrenheit. After 30 minutes, the cake's temperature is cooled to 140 degrees. So little t is 30, time is in minutes. And the temperature achieved for this part of the problem is 140 degrees Fahrenheit. So we replace the values with these specified numbers and we'll be able to find our K. So 140 equals 70 plus 210 minus 70 e to the minus k times 30. So 140 equals 70 plus 140 e to the minus 30k. And again, our goal is to isolate the exponential. So first we subtract the 70 from both sides. And we obtain 70 equals 140 e to the minus 30k. Next, we're going to further isolate the exponential by dividing both sides by 140. 70 divided by 140 is 0.5. And on the right side of the equation, we now have e to the negative 30k. We apply the natural log to both sides of the equation. So the natural log of 1/2 or 0.5 is the natural log of e to the minus 30k. And we know that the natural log reverses the operation of the exponential function where we made minus 30k the exponent, so we simply get the exponent. We divide both sides or all sides of this double equation by negative 30 to find our k. And we're able to approximate k at 0.023105. So when we approximate our function or do our next calculation, again our function is t equal c plus t0 minus c e to the minus kt, and we're now trying to find the temperature of the cake after 40 minutes. So we're trying to find T. C is still 70, the surrounding air temperature. The initial temperature is still 210. And now we know that K is negative 0.023105. And we're going to replace T with 40. And when you put this in your calculator, you have to make sure that this is parenthesized when you do this product between the negative k and the t. And so I'm going to put this directly into the calculator. So we get that our cake temperature after 40 minutes is about 126 degrees Fahrenheit. So after 40 minutes, the cake cools to about 126 degrees Fahrenheit. Here we have a function, another logistic function, that describes the number of people who have become ill. So F is the number of people who have become ill. With the influenza 2 weeks after its initial outbreak in a particular community. So T is the number of weeks after the initial outbreak. So how many people were ill when the epidemic began? So for part A, we are actually replacing T with 0. So we have 100,000 divided by 1 plus 5,000 e to the negative 0. And we know e to the negative 0 is e to the 0, which is simply 1. Negative 1 times 0 is still 0. And any non-zero number to the 0 power is 1. So e to the 0 is 1. So this is 100,000 divided by 1 plus 5,000, which is 5,001. So when the epidemic began, approximately 20 people were ill. So we get 19.996 and some more digits, and we're going to just round that to 20. So about 20 people were ill initially. So about 20 people were ill when the epidemic began. Now, the next question is asking me how many people were ill by the end of the 4th week. So it's asking me to find F of 4. T is the number of weeks after the beginning of the epidemic. So T is the weeks after the epidemic's beginning. So this is 100,000 divided by 1 plus 5,000 e to the negative 4. We're going to use our calculator. We have to make sure in using the calculator that we parenthesize this denominator when we do this calculation. So by the end of week 4, we've got 1,080 people approximately that are sick. So 1,080 people are ill by the end of the 4th week. What is the limiting size of the population that becomes ill? And that's always, so in other words, that's really saying as we allow T time to become infinitely large, so as t goes to infinity, we get 100,000 over 1 plus something that's going to 0. So in other words, let me write this a little bit different way. As t goes to infinity, f of t goes to, so in other words, e to the minus larger and larger and larger and larger number is becoming very, very, very close to 0. So as I look at this, it becomes 100,000 over 1 plus 5,000 times 0. So as t gets larger and larger and larger, e to the minus t is getting smaller and smaller and smaller. And we essentially get something that's 100,000. So that number in the numerator is always that limiting population. So the limiting size of the population that becomes ill is 100,000 people. And for these types of problems, the logistic model, that number in the numerator, is always the limiting size of your population. So this is a more realistic model. You don't have infinitely many people getting sick. The various factors of the disease and the community limit how many people get sick. So it's not, the amount of people getting sick doesn't grow in an uninhibited fashion. Uninhibited growth is an unrealistic model. So there's always something that limits a population growth. In this case, it's the population of people that are sick. So the logistic model is a more realistic model.